it will be by Girish Kulkarni, who will talk about physics of reionization. Okay, please. Girish.
Yeah, thank you, Suman. Okay, so the morning session was about understanding how the cosmological structure arises, and now what we want to do in the next 90 minutes or so is to understand how that structure connects to the intergalactic medium and causes reionization. So that's the plan for the next 90 minutes. I haven't, I have sort of a bunch of slides which are slightly disorganized, so I'll try to connect them using the board. And I hope all of you can read what I'm writing, etc. So to make a start then, I realize that not all of you are students of reionization. There are people who do continuum studies as well. So let's just make sure we understand what we are talking about here. So the idea of reionization is that we have excellent measurements of the ionization state of the universe at the last scattering surface because of the CMB, right? That's about few 100,000 years. And as soon as we understand the ionization chemistry at that point, it is possible for us to compute the thermochemistry from that point onwards because the universe evolves in a very simple way. Most of the evolution is adiabatic, and the adiabatic evolution leads to a universe which is completely dominated by neutral hydrogen. As all of you probably know, 75% of the matter content of the universe is hydrogen. And what happens soon after the last scattering surface is most of that hydrogen settles into the neutral state. Okay. Now, the problem with this understanding is that we actually happen to know, and we will see how, we happen to know from measurements that the universe today is not in a neutral state. In fact, we know that the value of the neutral hydrogen fraction XH1 is of the order of 10 to the minus. It's very, very small today. In fact, it has been small for the last 12 billion years. So we have observations to show that it has been ionized for most of the cosmic history. So essentially what must have happened is that if we try to make a plot of this XH1 versus redshift, let's say, we know that at redshift, let's put the 0 here and infinity there. This is our last scattering surface at redshift of about 1100. We know that at this point, the value of XH1 is very small, right? It's about 10 to the minus 4. But we know that at some point after 1100, let's say redshift of about 100 or so, XH1 was about 1, about 100%. And so something clearly must have changed the value of XH1 from fully neutral to fully ionized. Is that clear? That is the observational evidence that we have from reionization. I haven't described what observations tell us. I'm going to describe that in a few minutes. But then the goal of reionization studies is to understand everything about this process. Ideally, what we want to achieve at the end of square kilometre array studies and other studies of reionization is a plot which shows completely how this thing evolves. Okay, that also involves understanding what exactly was the process that caused it. So that's reionization for those of you who are new to the topic. A second quick concept which I thought Tirth will introduce, but he did not. So let me just make sure that all of us are aware of it, is the thing called the intergalactic medium, the IGM. So the IGM is technically all the matter content of the universe outside the virial radii of virialized halos. We have heard about the concept of virialized halos in the first lecture by Tirth. And there we also saw that there are things that have not yet virialized. And so if we look at the sort of one of these cosmic web diagrams that Tirth showed, which had this very beautiful filamentary structure, and we zoom onto any portion of this, what we would typically find is that there are these halos which have a well-defined virial radius. That's a concept that Tirth introduced. And what you call the intergalactic medium is everything that's outside these. Okay. Now, it turns out that the intergalactic medium actually holds the majority of the matter content of the universe. This is very important for everyone to understand. Okay, so the IGM is not a periphery of cosmological matter. IGM actually at redshift 6, it contains 90% of the matter content. Today, it contains about 60% of the matter, but at high redshifts during reionization, most of the matter is inside the intergalactic medium. Okay, so I guess that much is enough for the moment to understand. So when we say that the universe was reionized, it's mostly the intergalactic medium that we are talking about. Okay, it's an IGM problem, which is great because IGM is actually a beautifully simple system to study compared to galaxies. Galaxies have a lot of complicated astrophysical processes happening inside them. IGM doesn't have all this. So I hope these two words make sense to all of us, the term reionization and the term intergalactic medium. Maybe one quick comment I would make is that for many of us, including me, reionization itself is an interesting problem. We genuinely want to understand reionization, but there are also secondary reasons for why you might be interested in reionization. I'll just mention that so that you feel motivated to study reionization. So one secondary reason is, for example, the reionization acts as a screen between us and the CMB. So for a lot of cosmological studies that involve the CMB, reionization is a very important nuisance parameter. You need to understand reionization very well in order to study CMB very well. One of the important things one of the important examples of that is the studies of non-Gaussianity using CMB. Tirth mentioned non-Gaussianities in his talk. A second interesting aspect about studying reionization is because, as you will see in this talk, reionization is very tightly coupled to the thermal history of the universe, how the temperature of the universe evolves. And if you are a particle physicist, if you are an astroparticle physicist, if you are someone who models, for example, dark matter, typically particle physics theories always involve making some contact with the thermal history of the universe. So studying reionization is very important for studying those theories. That's the second reason. There is actually also a third reason, which also Tirth actually mentioned, if any of you grasp that, because it was a subtle point, which is that the thermal history, Tirth had this beautiful plot, affects the gene scale of the gas. He mentioned this. Now, gene scale of the gas is a fundamental limitation in our understanding of the small scale structure of the universe. And studying small scale structure of the universe is again important for studying dark matter. So again, if you want to study dark matter, you need to understand small scale structure, which requires us to understand reionization. Okay, I hope that makes sense. We have intrinsic reasons for studying reionization. It is in itself an important astronomical puzzle. But then there are also indirect reasons. If you are not interested in reionization for its intrinsic value, you might still be interested for CMB, for thermal history, or for small scale structure reasons. Okay, so with that introduction, I can start maybe using my slides a bit. So the first thing I want to discuss here is the topic of propagation of ionization fronts. Okay, now the question we want to ask is how could have reionization happened? What might have caused reionization? Okay, what was it that ionized and heated up this hydrogen gas? Okay, now the one thing that all of you should know is the answer is we don't know. Okay, nobody knows it. That's one of the ongoing research areas. However, a very conservative hypothesis is high energy photons, UV photons from galaxies did the job. Is this clear? I hope I'm making sense that this is still a hypothesis. Okay, don't let anyone tell you that we know that galaxies reionized universe. We don't. But it's a very conservative hypothesis. It's a very plausible hypothesis. All other hypotheses are slightly weirder. So the fundamental thing that we should study first is try to rule out galaxies. So the picture is that the hydrogen atom has an ionization potential of 13.6 electron volts, which is not much. It is easy to have photons with energy greater than that in astrophysical environments. This comes in the UV range. So if you have sources which produce UV photons, they could do this job as long as they are sufficient in number. Is that clear? Now galaxies have two mechanisms of producing UV photons. Okay, so if you have a typical galaxy, there are two mechanisms. One is stars. Stars in the galaxy, especially young massive stars, are very good at producing UV photons. Old stars are redder, so they produce less amount of UV photons. But young stars, O-type stars, for example, they live for only about 10 million years, but they produce a lot of UV photons. And we see them even in Milky Way, so we know they exist. The second way galaxies can produce UV photons is by means of a supermassive black hole. Okay, when each galaxy has a supermassive black hole sitting at its center. When these black holes accrete gas, they actually produce a lot of high energy light, not just UV, but also X-rays, gamma rays, but UVs as well. Okay, when a galaxy has a supermassive black hole that is shining, that galaxy is called active galaxy. Okay, and then the supermassive black hole is called active galactic nucleus. It's still a galaxy, but it's a special, for example, the Milky Way has a supermassive black hole, but it is not shining, which is why you don't see it in the night sky. It is a quiescent black hole. So these are the two ways. So again, we want to now, our hypothesis is, the first thing we want to study is the theory, the idea that it is galaxies that reionize the universe. Okay, and again, this is not proved. This is not proven. This is a hypothesis. But this is a very reasonable hypothesis. It's a good hypothesis to study. So now what we want to study is the physics of how galaxies might reionize the universe. Okay. So the simplest problem to start with is a single galaxy in the universe reionizing the region around it. So we have a very simple problem, no complicated situation of a cosmic web, etc. And even let's imagine the IgM to be uniform. So it's a very nice simplification. We have a box full of uniform gas, and we have a single galaxy sitting somewhere. What happens in this case is that what we want to ask, the question we want to ask is, this light, the photons coming from this galaxy will ionize some hydrogen atoms around it. And the question we want to ask is, what is the volume of the region that will be ionized? Okay, so that's the most basic version of the problem. And the answer to that is just this. Okay, where we have, imagine that the galaxy over its whole lifetime produces a given number of photons, Qi. It's a number, dimensionless quantity, a number. You can, for example, those of you who know population synthesis can integrate a population of stars and calculate it very easily in star formation theories. But if Qi is the total number of ionizing photons emitted by a galaxy, then if NH bar is that constant number density of hydrogen atoms in that volume, then if we just, the simplest equation we can write is this, where the volume of the ionized region multiplied by that number density is equal to the number of photons, because each photon will knock out one hydrogen atom. Okay, because there is nothing else happening. As soon as one photon comes, it's absorbed. There are no recombinations. So once the hydrogen is ionized, it just stays ionized. And so obviously the number of ionizations that is going to happen is equal to the number of photons available. Now let us start to make this picture a bit more complex. Our first approach is to try and understand a bit more the connection between that quantity Q with the galaxy properties, with the properties of the halos that Tirth constructed for us using structure formation theory. So for example, let us imagine that this galaxy sits in a halo with total mass mh. Galaxies always sit in halos. It's one of the biggest breakthroughs of galaxy formation theories pioneered by Jerry Oestreicher, that galaxies form inside halos. We have heard that from Tirth already. So imagine that the halo associated with the galaxy in our study, it has mass mh, and it has some baryon fraction. Let us assume it has the same baryon fraction as the cosmos, as the universe. So omega m by omega b by omega m. Okay? Let's imagine that it's a very representative halo. Now, as Tirth very nicely explained, we have a situation now where we have a halo with a certain amount of dark matter and a certain amount of baryons in it. Now the magic, complex magic of galaxy formation will take place and create a galaxy out of it. Now that's a very complicated process, and we haven't fully understood galaxy formation yet. People still have debates. But what we do know is that we have seen galaxies do have stars and gas. So we can imagine a very simple model where we assume that some of these baryons that were in this halo are converted into stars. And we can now assign it an efficiency F star, which means that F star fraction of these baryons go into stars. Okay, if F star is 0, then no matter what baryons you have, nothing will happen. If F star is 100%, then you have maximally star forming galaxy. But that is not enough because we want to produce our photons. So what we then do is assume that once a baryon is inside star, then per baryon we produce n dot ion number of ionizing photons per unit time. How do we know this? How can we model this? This is the job of a star formation physicist. So over the 20th century, many great people like Chandrasekhar have developed the physics of stars, and we now understand very well how stars produce light and heavy elements. Using that, you can easily, you get code packages now to calculate n dot ion for any stars, any scenario, any mass of stars and temperature of stars, etc. So given that, we can now assign a number of ionizing photons to per baryon. Now these are the ionizing photons which will be produced within the galaxy. The problem is, and this is not all students know, so I hope that this makes it clear for every one of you. Actually, when you do astronomy and try to find how many galaxies emit hydrogen ionizing photons, almost none do. If you went right now and checked nearby around the Milky Way, how many galaxies emit hydrogen ionizing photons, almost no galaxies emit any hydrogen ionizing photons. So how do we reconcile this with our understanding of star formation theory? The idea that we have is stars, particularly those stars which produce those 13.6 electron volt UV photons, are young. And because stars form from gas clouds, young stars are embedded inside thick gas clouds. And so the hypothesis we have is that these UV photons don't come out of the galaxy because they are consumed by creating ionizing bubbles within the galaxy itself. The ISM in the galaxy itself is consuming all the ionizing photons. So always remember this, galaxies are a really bad mechanism of producing ionizing photons, but unfortunately it's the only mechanism we have. Galaxies are so abundant that we do have that. Now I'm making a slightly extreme, drawing a slightly extreme picture. We do know of a few galaxies which are somehow successful in getting out some ionizing photons. Why? Sometimes in some galaxies, some violent thing happens and parts the clouds a bit, and there is a gap opened up so that the ionizing photons can escape. But this is definitely quite rare. In fact, there are many people whose careers are going into understanding exactly how rare this occurrence is. But I hope you get the point that there is no 100% chance that once you produce ionizing photons inside a galaxy, it will come out to do your reionization bubble. So we have another parameter here to quantify this uncertainty. We call it all famous escape fraction. All of you must have heard escape fraction last week in some talk or the other. What escape fraction means is that it is the fraction of the hydrogen ionizing photons that escape the galaxy and ionize the surrounding medium. It can happen that a galaxy has tons of baryons, it is producing tons of stars, stars are producing tons of UV photons, but the escape fraction is 0, and then the galaxy is useless for reionization. Is this clear? And we actually see these galaxies. There are many examples of really amazing, bright, big galaxies having 0 emission at hydrogen ionizing energies outside in our observations. Anyway, I hope these parameters are clear. But if we define these parameters like that, then the overall ionizing efficiency is this: F star times F escape times N ion. we give this a name, call it zeta. This is a very standard notation. You will see zeta in all of these theory papers on reionization. What zeta is doing is zeta is telling me how many ionizing photons come out to do reionization per baryon that went in. Okay? Great. So now what? Now what I can do is I can actually compute my Q, which I had in my simple equation at the start, in terms of zeta, because then it becomes a bit more physical. So I can now write Q as zeta times the baryon fraction, because zeta was the number of photons per baryon, and I know how many baryons are in my halo. It's just the halo mass divided by the baryon mass multiplied by the baryon fraction. So this is the baryon mass divided by the protons. So this is assuming everything is protons, everything is hydrogen essentially. I'm ignoring helium here, but you know how to change this equation. You just add the helium mass fraction if you wanted to, but that is not interesting for this lecture. Okay, but you understand, some of you might think this is trivial, but actually as an astrophysicist, we have taken a big leap here. We have connected that QI number to something that we understand, namely star formation. Okay, and cosmology. The MH, halo mass, and star formation are things well understood. So we have made that connection. So it's actually a big conceptual leap. Now what we can do is go back to the first equation where we had that volume, which was written as Qi by NH. And now I can calculate the radius of this region as simply the cube root of that. But now what I can do is I can actually compute this from numbers. If I had given you a Qi number, you would have calculated it, but you would have had no sense of what that Qi number means. But now you have some sense. So halo mass of about 10 to the 8 solar mass, which is roughly at the atomic cooling limit that Tirth explained at those redshifts. An escape fraction of 10%. This is roughly what observers have been reporting, about 10 to 15%. And NIN about 4,000. This is what you will get if you do population synthesis, like Starburst 99 or BPAS or something like that. And F star of about 10%. This is what simulations like Illustris are telling us. You see, now I'm picking up numbers which have been studied. There are people who have spent all their life studying just one of these numbers. Now I'm using those numbers rather than this Qi, and I plug it in, I get a number that is about half megaparsec. Okay, so already we have an insight that typically we should expect the ionizing bubbles to be about a megaparsec order of magnitude. Okay, but you can see this is really simple. What we have done, we have not done any radiative transfer or anything, we have just counted photons. So one insight you want to carry is photon counting is a really powerful idea in reionization. Okay, but now we have to quickly move on. We can't stick with this photon counting approximation because one of the most important things that we have forgotten is recombination. Okay, now what happens is that every time a hydrogen atom is ionized, there is a probability that it will again combine. Okay, there is a non-zero probability that it will again form a hydrogen atom. This probability actually has been calculated theoretically also. I think George Field has a paper doing this calculation using quantum field theory, but this can be measured in the lab as well. And then you get a number quantifying the probability with which this happens. Okay, this is called a recombination coefficient. It is called alpha B. You have to read it from a reference book. It is just a number and you have to keep it in mind. That number happens to be a function of temperature. If the temperature is high, the probability of the combination changes, but that's a detail. The point is there is such a thing as recombination. It's actually quite important. This number is actually quite large. So now what happens is I have that volume of ionized hydrogen, but it's not going to stay like that. At some probability given by this alpha B, the hydrogen will try to become neutral again. So now we have to change our theory to accommodate that. We can start by asking what is the rate at which that hydrogen will recombine. And we can say, well, the recombination is we need two entities, one proton and one electron to recombine. Number of protons is proportional to number of hydrogen atom because everything is ionized inside. Number of electrons is number of hydrogen atoms because everything is ionized inside. So Ne times Np is just NH bar squared. That's just this. The total number is that multiplied by the volume. And then we have that probability, alpha B, which we have taken from our atomic physics experts, right? That is just a number. You have to just look it up every time you want to do this calculation. But then now this gives me per unit time rate of this recombination. And now my equation changes. My equation says, well, what will happen now is, first of all, it becomes a dynamic equation now, because recombination is a dynamic thing. Unless you keep pumping photons, the bubble will collapse, vanish because of recombination. So now we say, okay, you wanted to sustain that volume Vp. If you wanted to sustain that volume, then you have to now continuously pump QI photons. So you have a QI dot now. Per unit time, you have to pump QI photons. How many photons? Exactly the number to compensate the number of recombination. So the number of recombination is this, alpha times n square times Vp. That should be compensated. Then we will have a constant bubble here. Okay? Now, that's one improvement to our picture. The other improvement is, well, before I say this, the calculation until now was actually done in the 1940s by a person called Stromgren. So the solutions that you get of the previous equation are called Stromgren spheres. These equilibrium spheres around ionizing sources in the presence of recombination. As long as the QI dot has the right value, which depends on the density of that bubble, the bubble will just stay fixed. If the QI dot is more than the density, the bubble will keep growing. If the QI dot is less, the bubble will start shrinking. Okay, and this is well known since 1940s. This is routinely seen in the Milky Way galaxies. If you talk to your optical astronomers or infrared astronomer friends, they actually observe these things even now to study stars and their spectra and properties. But now we are not in that situation, so we have to now do one step better than what was done in the 1940s. We have to do one step better than the Stromgren sphere. What we want to do now is to do a Stromgren sphere in an expanding background. Okay, so this is the new thing now. And so what we can do first is we will incorporate cosmological expansion, keeping recombinations in the analysis. And then we also relax our assumption that the source is steady. Let the source fluctuate, do whatever it wants to do. And then what we can do is we can get a very different equation now. Let's first read the equation and then understand what it is saying. What it is saying now is that because the universe itself is expanding, now that boundary of your bubble is not going to stay like that. It will move. It will either expand or shrink, even if you balance the recombinations. Okay, so now you can ask, well, how much will it change? So the first thing you find is that the first thing it will do is it will change in this fashion. So the density times velocity equals q dot times 4 pi r square. This is just like saying that the front will move a little distance dr. If that happens, then the new volume added is 4 pi r square dr. And so we now have new number of ionizations happening is 4 pi r square dr times nh bar. And then the q dot has to balance that. But this is not that q dot. This is a new q dot now. I have labeled it q dot fr. Fr stands for the front. This boundary is called an ionization front. And now qi dot front is only the number of photons that manage to reach the ionization front. Because not everything will reach up to the front, even if the internals are ionized. Why? Because many will be consumed by recombinating. Okay, you understand now? Now what we have done is we have let the source evolve, and then we are saying, oh, if the source in time dt produces qi dot fr times dt photons, then it will expand this bubble by the quantity nh times ui times 4 pi rp. Okay, this is the theory of ionization fronts. And there are many people, most famously Paul Shapiro, who studied this in great detail, the physics of these ionization fronts. In fact, if we now add the Hubble expansion, what will happen because of Hubble expansion is that NH bar will no longer be constant. So even if everything is balanced, the NH bar will evolve as a to the minus 3, where a is the cosmological scale factor, which Tirth introduced in his lecture. And if you do that, then you get a slightly different equation. Again, it's not too much different, but there's just one new term. This nh times dvp dt is the same term as before, the velocity term times nh. And then on the right-hand side, you have instead of qi fr, Now I have written Qi minus the photons consumed by recombination. So I have expanded the expression for QIFR. So Qi dot is the amount of photons being produced by the source, of which this is constantly swallowed by the region that is already ionized thanks to recombination. And whatever is left pushes the ionization front by this bit, dVp dt. But there is now an additional factor, which is minus 3 NH times H times Vp because of the Hubble expansion. The Hubble expansion lowers NH. So therefore, there is a negative term there. There is a minus 3 in the exponent here. Okay, so this is now the expression of a ionizing front evolution and ionizing bubble evolution in an expanding universe. What is important here is one can introduce a new quantity here, which is very important in reionization studies, called the clumping factor. If you had come to the IGM conference in Ayuka in December, there was a whole session dedicated to the clumping factor. So the clumping factor is as follows. The idea is quite simple, but it is quite important that we know it. The idea is that we have said that the recombination rate is proportional to the square of the density, right? You need one proton and one electron to recombine. Now the problem is, if the IGM is not uniform, if it has structure, if there are pockets of the universe where the IGM is much more dense than other pockets, then the average recombination rate is going to be higher than the uniform recombination rate, right? Because the recombination rate in the more dense clump will be square of the recombination in the average. It will grow. It is a non-linear function of the density. So as a result, now this is a complication, because this makes it actually very difficult to write an equation like this, where we have simply written density times alpha b. What we are saying is, okay, if the IGM is non-uniform, then the real recombination number could be higher than this actually. And so what we do, if we want to, well, one option is we stop doing this analytics and go to a simulation, then there is no problem. The non-uniformity in the IGM is just calculated by means of the hydrodynamics that Tirth described. But alternatively, what you can do is you can actually just say that, okay, what I will do is I can say that in overdense region of the IGM, the recombination is enhanced by a certain factor, which I will call C, standing for clumping. So essentially, this C is a fudge factor which takes care of this increment. This is quite interesting. You might, so at the mathematical level, this is a very trivial change. We have just introduced a factor. But it turns out that this is a very nice way to quantify the non-uniformity of the IGM, because you can now talk about measuring this C from observations, etc. And so people then debate about what the value of this C is. Some people say it is 5, some people say it is 10, etc. Okay. So next, if I do include this clumping factor, then my equation for the growth of the ionization front can now be written like this. We have the volume change of rate of the volume equals that Qi. I have now rearranged the density, so I have n bar h here minus the recombination term. So this is the amount of photons that are being produced. This is called the source term, and this is called the sink term. What I have done here is I have also changed from proper to co-moving coordinates, as a result of which I have got this NH bar 0, which is now the co-moving number density, and VC, which is the corresponding co-moving volume. So this is a very famous equation. In fact, if you want to quickly model reionization, you can do this in 3 lines of Python using this, and I highly recommend you develop intuition on this if you are interested in the problem of reionization. The idea is the growth of the ionization bubble is equal to the amount of photons produced minus amount of recombinations. It's essentially the same idea, but this equation correctly captures the cosmological expansion, etc., etc. Okay, this is also described as ionization equals sources minus sinks. This is a very colloquial way people will always describe this if you talk to the experts. So you can now solve this. Remember, we are still in the regime of a single galaxy ionizing a bubble. Okay, we still haven't done the reionization of the universe by many, many sources. But now we have achieved quite a bit of sophistication, because we have recombination, we have a fluctuating galaxy, and we have expanding universe. So you can actually solve that equation now. And these are some example solutions of that equation. I have just picked up this plot from the famous review article on reionization by Barkana and Loeb, 2001. So you are welcome to look. It's a very nice, important paper. What is shown here on the y-axis is a ratio V by Vmax, where V is the volume of that bubble. Vmax is the volume of the original bubble, which did not have recombinations or expansion. Vmax is the maximum you can do because there is no recombination. All photons are available to grow the bubble. There is no expansion, so the density remains what it was. And so this is that. And then on the x-axis is time. And the model here that they have used is a source that turns on at a certain redshift. The galaxy is switched off. It switches on at redshift 10. And then it shines at a constant luminosity for a million years. And then it suddenly drops off with some dependence on time, t to the minus 4 point. It turns out this is not a very bad approximation. This is actually how galaxies behave. When you have a sudden starburst, you have a lot of young stars, they shine. And once young stars die, they become supernovae. The galaxy UV luminosity drops very fast. This is how elliptical galaxies are formed. So this is now a solution of that. The top solution, which goes like that and settles at 1, is the one without recombination. You can see it settles at the Vmax. And then once you add clumping, it goes and it cannot reach the maximum and it comes down. If you increase the clumping, it again comes down again. You see, because the galaxy is switched on, the bubble also terminates. There are quite a few insights here. One is that you need to constantly pump photons in the IGM to keep it reionized. Just one burst of photons will not do the job. And the other is that the clumping factor matters. It does have a strong effect on the evolution of ionization. One interesting comment I will make, and actually those of you who are interested in fronts, Anson D'Aloisio, Paul Shapiro, these people write very beautiful theoretical papers on these calculations on fronts. You are welcome to do it. I'm not an expert on that. But there are curious things that happen. For example, in these equations, if the source is made very bright, the velocity becomes speed of light. So you have to then handle that. There are interesting things, a relativistic correction has to be made. I'm just mentioning this. This doesn't happen typically, but it can happen at very early times if you have a bright quasar. There are also interesting effects when in early stages of that evolution, the front is actually faster than the speed of sound in that medium. Then interesting things can happen. Then people have phenomenology of these fronts, R-type fronts, D-type fronts. If you're interested in ionization fronts, there is a very nice amount of literature about that. But at the moment, of course, we don't have time to get into that. So I will just go and mention here that this is a very nice, simple calculation. Bubble growth equals source minus sink, and it describes the bubble around one galaxy. Now, of course, what we want to do is not this, but a real universe which has many, many galaxies sitting in many, many halos. We might keep the parameterization still the same. Each galaxy has a certain F star, N dot, your F escape, and so on. But the critical change we are making to the story is now there are many, many galaxies. There is no longer just one galaxy. Now, this becomes a very complicated problem because we know that the galaxies are distributed non-trivially. They are distributed according to the structure formation theory that we heard. So we have to make sure that now our calculations remain true to that structure formation theory. And that becomes a bit challenging. Okay? Everyone understands the problem that we are trying to solve? We have solved this problem. Now the problem we are trying to solve is there are many, many galaxies, each with some ionizing bubble. Right? The standard picture that those of you who have worked on reionization must have seen in your own work, others might have seen in talks, etc. Now we want to calculate this. And as you should appreciate quickly, it's not as straightforward. It's not going to be as straightforward. So what we do is we split this problem into two. Fundamentally, the whole field, even observers split it. We actually think of it in two ways. We first do the simpler bit and then also talk about the complicated bit. The simpler bit is what we call the global ionization history, in which we say, okay, I don't want to study the complicated bubbles at the moment. Just tell me total fraction of neutral hydrogen. Okay, just total fraction, which is what I started the story with, this XH1 over the whole cosmological volume. Okay, just tell me that one number for the whole universe as a function of redshift. Does everyone appreciate the simplicity? Right? And then the second question is, okay, I'm not satisfied by the number. I want the full details. Okay, this is called morphology. The morphology is a much harder problem, actually. Okay, and this is harder in all levels. Even SK, people say SK level 1 will first do global history. SKA phase 2, if it happens, whenever it happens, we'll do morphology. This sort of discussions you will find. Theoretically also, people will say, okay, we have a lot of problems modeling morphology. Let us see if we can model XH1. So I hope you understand. So we will quickly discuss first the global ionization history first. So our goal now is to discuss just the evolution of this XH1 and how to model it. So now the idea is actually we again do photon counting. We say that one photon ionizes one hydrogen atom, modular recombinations. So how would this look like? Well, now the problem is we don't have one galaxy sitting there producing, right? But do we have a sense of how many galaxies there will be on average? Yes, because Tirth has developed for us a very robust mathematical framework for understanding how much matter is inside halos at any one time. You just integrate on the halo mass function that he derived, right? If you want, you can use that Press-Schechter mass function or Scheidt-Tormen mass function, or if you don't trust either of those, you can do the simulation. But we know how to do it, right? That quantity is called F collapse, this thing that is sitting here. This is the amount of, the reason it is called collapse is because the halos collapse. So this is like referring to what fraction of cosmological matter is inside collapsed halos. Here, the small twist is it is inside collapsed halos that are capable of reionizing. So very small halos might collapse, but might be useless for us. So now what I can do is I can replace that one galaxy's property. That one galaxy had quantities like M halo, remember? M halo multiplied by omega baryon. We throw away that and just have F collapse. And we multiply that with zeta. Zeta remains zeta. We are assuming that all galaxies have same escape fraction and ionizing efficiency. We multiply by zeta, and then that gives us that average. Okay? So Q here, very famous quantity in notation in reionization, is the fraction of cosmic volume in ionized regions. Zeta is the number of ionizing photons per baryon, and F collapse is the fraction of matter that is in halos that can produce ionizing photon. You can immediately see why theoretically it's much easier to talk about XH1 than morphology. Morphology would involve me actually doing all that clustering and who knows how to do it correctly with the zetas, etc. But here I have already solved the problem under the assumption that all galaxies are alike. I have the same zeta. But now what we can do is we can add recombination. The idea is we just assume that each ionizing photon produces an ionized bubble and these bubbles overlap to produce QH2. So what we can do is we can just start from the equation of that single ionized region and sum over it over for all bubbles. And that gives us an equation. Again, as soon as you add recombination, you have dynamics because recombinations is a per unit time thing. So you can do now an equation which is dq dt. So at what rate will your ionized fraction evolve, which is again source minus sink, except the source will no longer have that galaxy. It doesn't have that qi, it has F collapse. And so what is done here is we have taken the derivative of F collapse where we are saying F collapse changes because the universe evolves. So newer halos form, which means new galaxies form. As soon as new galaxies form, you have new zeta sitting there, okay? Minus recombinations. And the recombinations are averaged now over the whole box, and therefore we have to add the clumping factor because averaging will otherwise be wrong because of inhomogeneities in the IgM density. Okay, this is called the one zone model of reionization. Okay, this is just one equation. You can in Python solve it in 2 lines and it's really beautiful. If you tomorrow see a JWST paper with new galaxies, you can quickly fire up your Python and compute whether those galaxies will reionize the universe or not by just calculating this. And in fact, this is how the solutions will look. You have QH2 as a function of redshift. This goes, I didn't even bother to write down the parameter values because they are not important, but you can see that QH2 is starting from a very small value and at some redshift reionization is completing, and different curves are for different values of zeta and maybe clumping factor as well. Again, this plot is also from the Barkana and Loeb review, so please do take a look at it if you want to understand the great details and the whole derivations. Okay, so it was easy to solve XH1. We could just get away by writing one zone equation. So now we have to talk about the remaining bit, which is the morphology. Okay, so how does the how do we do the morphology? We say that the region of the IgM is ion. So you might think morphology is really hard, and indeed, in some respects, it is the hardest thing. But it turns out that even at the morphology level, there is a lot that one can do using analytical methods. Quite remarkably, actually, I don't think I would have guessed it. It always surprises me how powerful these methods can become. So I will describe one such method. There are a few other alternatives on this as well. So the idea is as follows. What we say is that now we say a region of the IgM is ionized if the number of photons there is greater than the number of hydrogen atom, which just gives us this condition. Zeta times F collapse within that region, where the region has size R, the region is at redshift Z, and the region has overdensity delta R. So it might not be a representative region of the universe, it might be an overdense part of the universe or an underdense part of the universe. But we are saying if the amount of matter that was in it was F collapse, then all you have to do is compare the number of photons with the number of hydrogen atoms, the mass cancels out, and you are left with just the zeta and the F collapse. And as long as this quantity is greater than 1, then this particular region, which has size R and overdensity delta R, ionizes. But this is not the end of the story quickly, because the problem is regions are not ionized by galaxies only inside them. They are also ionized by galaxies outside them. So that is completely missed here. Okay, and this was a big challenge actually for analytical modeling. But before we get that, one quick thing is adding recombination is really easy. You just scale the number of photons by the number of recombinations in the assumption that the recombinations are uniform. If recombinations are non-uniform, even adding recombinations here is a bit complicated. You can read, I think Tirth has a nice paper recently on how to do it in his code. You can read the equations there. It can get a bit, although the physics is very simple. You again have to fold in that recombination term. But how to fold that here turns out to require slight work. But in any case, let us for this lecture assume uniform recombination, in which case adding recombination is also easy. So the problem we are left with is that problem, that regions are ionized not just by galaxies within them, but also by galaxies outside them. So what is absolutely remarkable is that this problem can also be solved using the same excursion set method that Tirth used to solve the halo formation problem. He had these barrier crossing and excursion sets, which he invoked to write the mass function of halos. It turns out that you can cast this problem in exactly the same way. Now, how to describe how to do it requires some thinking, and I encourage you to read the textbooks, but the basic intuition is not that hard. See, what happens in halo formation is that you have a bit of an overdensity at one point, and therefore that part is likely to collapse into a halo. But this whole region might be in a much bigger overdensity, which also collapses. Or this could be in an underdensity, which is then going to collapse later than similar mass halos in other parts of the universe. This is exactly similar to ionized regions in one part being sensitive to a larger thing. Okay, so I'm doing a very hand-wavy intuitive picture here. For the rigorous treatment, you really have to read up these papers. But it turns out that this kind of very hand-wavy mapping between the ionization problem and the halo formation problem really does work. And when it works, what happens is that this delta R, the overdensity that was sitting here, you can actually cast that equation into this kind of an equation where the condition now becomes delta R greater than some quantity delta B, which has the zeta sitting in it. Now this condition is interesting because this is a barrier condition. You can now you can just transport the whole technology from halo model to do bubble modeling. You can write a bubble mass function, whatever that means. You can write bubble merger rate. You can write bubble bias. You can write bubble power spectra. All of that just goes through. This is called barrier. In fact, there are many, many papers. You will see people assume, let us assume a flat barrier, this barrier, that barrier, top hat barrier. People have gone wild with the mathematics of this to develop intuition for how this works. But the important thing is this barrier is now a function of that ionizing efficiency. The galaxy physics is sitting in that barrier. It is really amazing for those of you who are actually struggling to understand what just happened. We were doing photon counting and suddenly we have got into a barrier kind of discussion. I sympathize. It is actually a bit of a weird jump. And the fact that it works is quite remarkable. So now we can do all sorts of bubble cosmology. In fact, this is a calculation from this kind of a thing, where what is calculated here is in some sense a bubble mass function. So on the right hand, on the horizontal axis is the bubble size R, and on the vertical axis is the number of bubbles at that R multiplied by some quantities to make things dimensionless, etc. And you can and the different curves are for different astrophysical, different zetas, different parameter values. And you can see that, for example, for some models, most bubbles have a size of 100 megaparsecs with this particular shape. I can see the shape is non-trivial. So there is a lot of physics here. Or for example, this model, whatever it is, not important for this discussion, has very small bubble and so on. But it's quite remarkable that you can do this calculation. In fact, the code 21 centimeter fast does this. When you run 21 centimeter fast, the bubbles are produced using this set of excursion set thing. So that's as much as analytics can do for you. Okay. At this point, if you want to do better, if you want even more reliable calculation, you really want to face the fact that essentially the physics of this is not bubbles or photon counting, it's actually radiative transfer. It's a very mature part of astrophysics, a famous book by Mihalas, full of radiative transfer mathematics. Chandrasekhar has a book on radiative transfer. And the idea now is you literally have to solve the radiative transfer partial differential equation going away from sources into the IGM. Okay, that's the ultimate problem. So we will. You have a special lecture on radiative transfer techniques, but I will quickly give you a taste of how radiative transfer techniques deal with the problem, so that you can compare with the ionized. So the radiative transfer equation is this. Is there a question?
Yeah. There, when you are taking the clumping factor, then you are taking it a single value for a certain galaxy or something like that. So when you do this morphological thing, do you give a single value, or do you give, depending on the electron density variation scale, you give different values within the same bubble?
Yeah. So the clumping factor value is always a single number. And the reason you got a bit confused is that the clumping factor has nothing to do with the galaxy. It's an IGM quantity. And therefore, and it is actually a, what is it called in statistical mechanics? Extrinsic quantity. It is actually a quantity describing the full volume. So it's always one number. We can debate about whether using one number is right or wrong. That's a separate discussion. But clumping factor is always one number in any treatment. No, if you have multiple bubbles, the clumping factor will still be 1 for the whole box. Yeah, the clumping factor is always just one number. That is the criticism of clumping factor, that how can such complicated things be captured by one number? But it's also its beauty that within one number, it does much better than the 0th order thing of no clumping. So the clumping factor is an IGM quantity, not a galaxy quantity. Okay, so I think we should move on a bit. So yeah, so now the next bit of physics is really going full rigorous and just saying, okay, I have done as much as I can do with simplified techniques and smart theoretical tricks. And what we have to then do is we really have to solve the radiative transfer equation. Now the radiative transfer equation is a standard equation in astrophysics, which has a lot of interesting books. Rybicki and Lightman is the main book that is recommended if you want to understand this. Now in the cosmological context, this equation looks like that. The first thing to note is it is a partial differential equation in several variables: spatial variable, time variable, frequency variable. And it might be difficult to read the equation, but it's conceptually pretty simple. You have to imagine the fundamental thing in radiative transfer is a concept of a ray. And the idea that in radiative transfer, there is a quantity which does not change along a ray unless there is some absorption or emission, namely specific intensity. You can define such a quantity, that's I nu. And now you write a partial differential equation along that ray. Okay. And the equation has various terms. The first equation is how does the intensity change at each location with time? Maybe because the source is fluctuating, maybe because of the density is fluctuating, maybe because there are velocities, something. Second is how does it change in space? How does the intensity change along that ray? Maybe because the density has a profile or something. And finally, there is a cosmological expansion term. There are two pieces there. One is because the volume is expanding, and the other is because the photon wavelength is expanding. Then, so that's it. So this is talking about how that specific intensity is affected. If there is no astrophysics, then that's it. That whole thing is equal to 0. In fact, if there is no cosmology, then just this bit is equal to 0 is your full radiative transfer equation. But of course, what we want to study is a situation where there is absorption and non-trivial things. And then we get these two new terms. The first of these terms accounts for the absorption of this light along the ray. And the second term is accounting for emission of this light along. Why would light be emitted along the ray? Because of recombinations, for example. Hydrogen might recombine and combine and produce photons, and those will have to be accounted for as we go along. So this is the full equation. Now, this has to be solved. There are many, many ways to solve this. In simulations, you will find people have done really amazing work. In fact, Ilian is not in the audience. In 2000, I recall, was it 2010 or 9? He ran this big project called Radiative Transfer Comparison Project, where he went around the world and collected everybody's methods and did a systematic comparison on a specific set of problems of how their methods to solve this equation compare. We will just study, so I cannot tell you all the methods, but there is rough categorization of these methods, which I will quickly say. One method is what is called ray tracing method, in which what you do is you do the kind of cosmological simulation that Tirth showed. You place galaxies, these sources inside halos, and you trace rays, actually geometrically trace lines, and along each line you solve that partial differential equation using some numerical methods. Okay, here examples are C2-ray, Licorice, Crash. We heard C2-ray and Licorice in the conference last week. In fact, the author of C2-ray, Geralt Mellema, was there. So these are codes doing ray tracing. And there is another method which is slightly newer and which is slightly non-intuitive. And these methods are called moment-based methods. And what these methods do is that they actually don't solve that full partial differential equation. They actually solve certain approximations to that equation called moments. So they do a bit of cheating. Instead of solving the full equation, they solve averaged versions of it. Okay, but they do it in a way that they actually match this. One amazing thing actually is the scaling of these two class of algorithms. One ray tracing algorithm scale as the number of cells and number of sources. This is a big problem because in reionization, the number of sources are billions. So C2-ray and similar codes are great under normal circumstances where there are maybe a few galaxies and you are studying something in the ISM. But when you want to study reionization, where you know that the whole box is full of sources, when you want to model your square kilometer array signal, then you need moment-based methods, because in moment-based methods, the moments are taken in such a smart way that the dependence on this number of sources goes away. So it doesn't matter if you have a billion, trillion sources, the code doesn't slow down at all. Example codes here are Aton, Enzo, RT, ART, etc. So mostly there are just these two categories. There are one or two codes which try to sort of the hybrid versions. Is a very nice code called Traffic by Yopche, but those are isolated examples. Generally, whatever radiative transfer you see will fall in these two categories, even if I have not listed all the codes here. Okay. So I guess what I will do is I'm at the 1 hour mark, so I have about 30 more minutes. So what I will quickly do is quickly go through how these moment-based methods work, and then I want to start wrapping up. So as Tirth said, we can neglect the Hubble term at high redshift. So just to keep it simple, and so for this discussion, I mean, we don't have to do it in the code, but then what we have is a slightly simple looking equation which you can do calculations with. It's essentially the same physics, however. And now what we do is we take angular moments of this. What does angular moment mean? You basically, the 0th angular moment of any quantity is the average of that quantity on all angles. Okay, so for example, I multiply it by d omega, which is the area element on a sphere, and I integrate that quantity on that spherical surface and divide it by 4 pi. This is called the 0th angular moment. The first angular moment is you first multiply it with a unit vector on the sphere, the area vector. Then you have a new quantity, which is a vector quantity or something, depending on what the original quantity was. And then again, you integrate on the sphere and divide by 4 pi. And so now what you can do is you can do this 0th angular momentum, first angular momentum, second angular momentum, third, fourth, fifth, as long as you want to go on that radiative transfer equation. What happens is people actually did this not now for reionization. This was done in the 1960s. There are beautiful papers. In fact, even now people use this method very powerfully in neutrino physics. They do neutrino transfer equation, just like radiative transfer equation. And they really, there is very rich theoretical literature on these moment-based methods, because as soon as you take these angular moments, something rather remarkable happens. If I take a 0th angular moment, that equation, which was equation in I, becomes this. Now this has no I, no specific intensity. It has got a new quantities, namely n, which is a photon number density, number of photons per unit volume. Okay, this is just the first angular moment of that specific intensity. Okay, and we have flux, new quantity coming here, f, which is that multiplied by n, which is the first angular momentum of the specific intensity. So just taking the 0th angular moment gave us an equation like this. Note that on the right hand side, the equation looks still quite similar to before, except again that the I is replaced by n. It is still kappa and j there. Okay, we can continue actually. We can do first angular moment. Now what happens is that the first term where we had n, now we get f there. We get a flux, because remember first angular moment was first making it a vector. So we have a flux, which is a vector. And the second term, which was a vector, now becomes a tensor, because it gets two n hats. And this has a name. It is called a pressure tensor. No need to worry about what about it is pressure. There is an interpretation, but it's not important for this discussion. And on the right hand side now, we have got again the flux. Okay. So what we now see is that this new quantity has come up called the pressure tensor, which has two copies of that n vector. So this is the second moment of the intensity. Now, the problem is, if I want to solve the 0th order equation, I need flux, because it sits in the second quantity. So then I solve the second equation, which was my first moment, but that has P, pressure. So I need to solve for that. That will require the next higher order, which is why you will actually need to solve infinitely many equations, which is not surprising, because you should actually be required to solve the real equation. The problem, however, is someone actually found a really clever trick. They said that at the third order, let us make an assumption about the pressure tensor. Let us by fiat write down a form and plug it in, and let's see what happens. And there is a lot of discussion on what form works. In fact, if some of you are interested in working on this, please talk to me, because I have some suggestions on how to come up with better forms, but I haven't found the time to work on it yet. But one person, Livermore, in 1984, found one particular form called M1 closure. This form, this is now a formula for that pressure tensor. It's just granted. It's like, take this. I want to stress that this is completely pulled out of a hat. It has nothing to do with our reionization problem. The remarkable thing is, when we plug, and that formula looks like this, okay? Where are the quantities are some? So you see, it's a really strange combination. It's like some cryptic symbols thrown at us by this person from the 1980s. This actually has some physics interpretation. In some Lorentz frame, a black body emits with this pressure tensor. But again, that has no connection with reionization. Reionization doesn't have black bodies moving at relativistic speed. And so indeed, oops. Now what we can do is you can plug that in and solve your equation. So what you can do is you can put these sources and draw these sight lines from these sources. And then along these sources, along these sight lines, you solve not that original equation, but these moment equations. Okay. So for example, in my work, I have been doing this using a code called Aton, which was developed originally by a group in France. Just to recall, our equations now to solve, the task is this. Okay. The other thing is, these equations are now local equations. They are not along rays. Number density, in each cell, there is one number density. And as long as you have the value of flux in that cell, kappa in that cell, and J in that cell, I can just remain in that cell and solve these PDEs. Okay. So this represents an initial value problem with PDEs. Now, if you open any numerical methods book, there is well-known techniques to solve initial value PDE problems. Simplest method is explicit Euler. So we don't even go for fancy methods. We use literally the most basic method, which is the explicit Euler method. One catch there is Euler method for PDEs. We know Euler method for normal ODEs. It's crude, but it works. So we usually use it quickly. And then if we are desperate for accuracy, we use Runge-Kutta or some such higher order methods. But at least it works. It is inaccurate, but it works. For PDEs, Euler actually just collapses under certain regimes. It works, and then when it doesn't work, it just gives garbage. And this, where it works and where it doesn't work is quantified by Courant condition. It depends on the time and the spatial resolution of your Euler solver. So as long as you have to maintain that, as long as you maintain that, you are able to do it. So now the full reionization problem, we go from those photon counting situation to a set of equations like this, where we have these two equations representing our moment equations, equation representing n, number density of photons, f, flux of photons, and then of course what we have not discussed is the non-radiative part, which also we have to do, which is the chemistry part. What do these photons do to the hydrogen? They do the ionization, and then there are these recombinations happening. Those are these equations. This is the hydrogen ionization equation, and what I haven't discussed yet is the associated effects on the temperature of the IgM, which is this energy equation. So we typically refer to this as the thermochemistry equations, and this is the radiation matter interaction equation. This is what is quantifying the connection between your sources and the IgM, and this is quantifying the connection between the radiation and the IgM. Okay, so these are now your equation. As long as you fulfill the Courant condition, go ahead and solve them with an Euler equation. You can discuss the accuracy and property. You can try to solve those problems now using this method and compare it with those photon counting approach, and it all works very nice. These are all Stromgren spheres, etc. But then ultimately you get to something like this. What is shown on the left panel here is the neutral hydrogen fraction, and on the right panel is the temperature. And this is being solved by this moment equation. And at least intuitively, it does feel like it's doing what we want it to do, right? There are these bubbles forming along these galaxies. But now you can see there's a lot more detail than what we had in our simplistic source minus sink equation. Okay. You might say, okay, so this is the 100% foolproof problem. Well, this also has approximations. Our galaxies are still simple. They are still these zeta elements sitting there emitting photons. Okay, this still is very poor in terms of galaxy formation. There is a second important drawback of this approach, which is radiation hydrodynamic connection is not there. So this radiation should actually, because of radiation pressure, push on the gas. So in principle, what you should do is radiation, gravity, hydrodynamics, radiation self-consistently. This is so expensive that only a few simulations exist. I think one such example is the CODA, Cosmic Dawn run, which Ilian does. So you should talk to him about that. And then the second run is, the second example is Thyssen, which is the Harvard MIT group, Vogelsberger and others. But you can, as you can see, there are just one or two examples. In fact, Cosmic Dawn, their first simulation did not work out. And then it took years to get the second model because it's just so expensive. But that is a drawback that is not being represented. But otherwise, this is what is capturing the full physics. This is what you could consider an ab initio model. Okay, I could go into the performance, etc. Let us not go into that, but let us move back to my original presentation and continue what I wanted to say. Okay, now we have studied two methods of doing the physics of reionization. One was these analytical methods, which were beautiful and powerful in terms of intuition, but they were analytical methods, so they had to make lots of approximations. And then we studied this sophisticated numerical method where we actually just attacked the real problem of radiative transfer, albeit with some approximations as a result of moment making. Now it turns out that people then started wondering whether there is something in between, because these full simulations are really costly. Okay, in fact, each of those simulations costs about 70 to 80,000 rupees, as I was telling someone over coffee. And analytical simulations are very easy to do, but they don't have the enough details, right? So an effort started in around 2004 or 5 to see if we can learn from the full simulations and tweak our analytical methods so that they remain analytical. They might not any longer be as beautiful as our simple analytical methods were, but they remain analytical. And this effort has now grown into a big industry. This approach is called semi-numerical modeling of reionization. Okay, so a famous example of this is 21 centimeter fast. But there are other examples. Tirth has a code called Script, which many of you might have heard of. There are many. I think Reion Yuga is Rajesh's code. And then there are quite a few such codes that people have made. In each of these codes are much simpler. They never solve the radiative transfer equation. They still do that photon counting, but they do it at a level of sophistication much higher than what we did. They are a bit intermediate between our level of analytical thing and the numerical thing. Okay. But the basic, so describing these in details would be a long lecture. I encourage you to read the papers. But what I want to give you an idea of how the philosophy is, because conceptually these methods are quite simple. So I want to give you a framework so that if you are interested, reading these papers and using the codes would be quite easy. So the basic idea is you start with initial conditions, cosmological initial conditions, exactly like a normal simulation. Except next, instead of evolving this density field to nonlinearity using normal simulations, you do something simple, which is analytical. And we have already learned techniques in the morning lecture, namely Zeldovich or Lagrangian perturbation theory. So yeah, you do Zeldovich. If you have a bit more time, you do 2LPT. But Tirth very nicely showed these plots where Zeldovich also looked quite good when compared with full simulation. So Zeldovich is not bad at all. So you do that. Then you identify sources. Again, you identify halos, either via barrier crossing or some such thing, which is where you will put your things, your galaxies. And then what you do is you calculate morphology around these sources in the presence of inhomogeneous recombination. And that is done using the single galaxy problem. You can now do it using that sort of photon counting mechanism. The details vary. Okay, so 21 centimeter fast does that steps in one way. Script does it in a different way, and the details are messy, because remember what is being done here is somehow mimicking the full simulation without doing the full simulation. So the details are messy, but I hope the idea is very clear. Start from initial conditions, don't do a cosmological simulation, do Zeldovich or 2LPT, identify sources and do photon counting in some smart way. And keep an eye on whether this compares with full simulations. Once it compares, you have a successful semi-numerical model. Then you forget full simulations. You use it in various ways to do reionization calculation. In fact, there are many papers which have tested these models in comparison with radiative transfer. They compare really well. There is only a difficulty in the period after reionization is finished. Once reionization is over, that is where there is a bit of a problem. But until then, it's all okay. There is another difficulty is if the sources have weird spectra, then these models struggle a bit. That's a technical point. Unless you are really working in details of reionization, it shouldn't concern you. That's a very minor caveat. So these are all the ways in which the physics of reionization can be calculated. I think we have about 15 minutes. I could go on a bit, but maybe what I will do is ask you if there are any questions.
Hello.
Yeah.
Yeah, so just needed a small clarification. So in the radiative transfer equation that you wrote, there was a grad I knew term. So is it something similar to refractive index variations?
So in a sense, yes, because it actually represents the velocity of the front. But it's actually the velocity of the front rather than the photon. So in the sense, intuitively, that is exactly what that term is doing. Actually, the way I think of that term is viscosity terms. I didn't emphasize it, but I should have. Those two equations, the n equation and the f equations, they are actually Euler and continuity equation. So essentially what we have achieved is we have turned the photon field into a fluid. And in fact, this is what happens when reionization finishes in those boxes. You see light sloshing in the box. There are waves because it really is fluid dynamics equation. So that equation is a damping term, is a viscosity term, which is essentially refractive term. So you are absolutely right. Okay, any other questions? Otherwise, I can keep talking for 15 minutes and maybe say a few more things that might be of interest. Okay, so maybe I should just proceed. So there are quite a few things on which we have actually finished our main agenda of modeling reionization. I hope you appreciate that. We started with a system which had IgM and galaxies, and we now know mathematically how to connect them at various level of accuracy and rigor. But now maybe, so now what is remaining is actually a peripheral discussion. So there are two types of things that I could discuss, and I'm not going to be able to discuss everything, but I will sketch maybe how you should think about this beyond reionization modeling. Is you can think about what happens in the post-reionization universe. When everything is reionized, what happens to these equations? What happens to reionization physics? That could be a discussion to have. There is a discussion that we can have in the pre-reionization era, which we refer to as cosmic dawn, right? What Saras and Edges and Reach are trying to detect. So this is before the galaxies start producing these UV photons. And then what we can turn into is, if I add now what we have discussed, which is the epoch of reionization, then what we can discuss is the physics of various probes. That is a very fancy discussion. How does 21 centimeter physics work in this technology? How does Lyman alpha physics work? How does X-ray physics work? Lyman alpha emitters, all the intensity mapping and all that things. So what I will do is I will make a few remarks on the post-reionization epoch, and then maybe we stop. Post-reionization epoch is important to understand because it gives us continuity. There is a boundary condition. Your reionization calculation must end up with post-reionization epoch, because the post-reionization epoch is extremely well measured. And it is measured using the technique of Lyman alpha forest. And Lyman alpha forest, for those of you who are not aware, is an extremely precise measurement. If you have any paper using a Lyman alpha forest measurement of a quantity, the error bar is very small. It's a very reliable thing because it's a very robust and easy quantity to measure in a telescope. The restrictions are strong at the end. In reionization, if you make a mistake in your recombination terms, because the data quality is not that great yet, it's okay. But post-reionization, the conditions are very stringent and you must actually reproduce the observed universe there. So therefore, we should make some remarks on how that works. So the first thing you have to remember is, it turns out, this is an empirical fact, it need not have been the case, is that the post-reionization universe is in ionization equilibrium. It turns out that galaxies continuously produce abundant photons to constantly balance recombinations from about redshift 6 to today. Okay, so that the universe has been consistently ionized throughout that period. Okay, and this is very well studied. This is a very good review article is by Mike Singh, Avery Mike Singh. I think it's 2011 or 10 maybe, but it's in other review articles as well. So this is not where there is much openness left in terms of understanding. So what is ionization equilibrium? So now if in the post-reionization universe, you go to any location and you calculate the number of recombinations, which is this recombination rate times number of electrons times number of protons, it is now equal to the number of neutral hydrogen atoms multiplied by something. What would this something be? This would be something that is now related to that zeta term. But the problem is, now this thing is related to all the galaxies in the observable universe. Because now reionization is over, so UV photons can travel the whole extent of the universe. So any typical point in the universe now sees all the galaxies. When this happens, the appropriate mathematical technology to use is that of the photoionization rate and fluxes, which is the language developed in, again, radiative transfer literature. So what we can do is we can write a quantity called photoionization rate. It just means how many hydrogen atoms are getting ionized per unit time. It is a measure of the radiation intensity at that point. So this equation is trivial. It is just saying number of ionization is equal to number of recombination. The only thing that has changed from before is now our Qs and zetas have been replaced by this capital gamma. Okay, because Qs and zetas were appropriate when we were seeing only a few galaxies, but when we are seeing the whole box, what is appropriate is gamma, because gamma can be actually calculated and connected much more easily to the observed number density of galaxies. And the connection is as follows. This gamma is related to this quantity J, which is the specific intensity of UV photon. Okay, essentially what is being done here is gamma is saying, okay, how much flux you have at my point where I am, then there are some atomic physics and geometry factors. Multiply that by the cross section of the hydrogen atom and integrate it over all relevant energies. That's the number of ionization you have per unit time. Okay, so this becomes the photoionization rate. The beauty is there is a very simple analytical formalism for writing J in terms of epsilon. What is epsilon? Epsilon is the volume abundance of galaxies producing ionizing radiation, which is something that we can just measure. We can count galaxies. So now we have connected our IgM to the galaxies. All of these are essentially, so this bunch is just cosmological factors having to do with redshifting and expansion. This is slightly non-trivial. This is accounting for the fact that from each of the galaxies in my volume, the radiation is dampened by recombinations happening along route. Okay, and I have to do it in some way on an average, in an average way, and this is done using this effective opacity. So those of you who have seen the Hart-Maddow, famous Hart-Maddow paper or similar papers, what they do is they compute these things by actually going to various surveys and calculating epsilon and going to various surveys and calculating tau effectives. They actually measure these two quantities using astronomy. They combine it and plug this equation, and then what you get is actually, looks like I have, and then what you get is actually this result, which is a result of that kind of a calculation. What is shown here is this quantity J as a function of lambda. So this is the typical spectrum of radiation at a typical point in the universe. This is actually calculated from observations by measuring epsilon and tau. Okay, and what is happening at these, why does it have these steps at these redshifts? Because this is the hydrogen ionization break and the helium ionization. So as soon as the spectrum hits hydrogen ionization energy, higher energy photons are gone in equilibrium. But they're recovered. Why? Because the cross section goes down at higher energy. So very high energy photons are not very good at ionizing, even though they have high energy. And so then you have some flatness, but then you hit helium ionization front, and then again you collapse. And then again you recover in some way, and then that recovery has to do with. But this is called the UV background. We will see people talking about the UV background in post-reionization universe, and you can measure this all the way until today. Okay. Okay. I guess maybe just one bit I will mention is that now in this post-reionization universe, you are left with this fluctuating IgM in ionization equilibrium with this spectrum, right? You can actually model this, and this is called the Lyman alpha forest. Okay, it looks like this. This is from a simulation. The bottom is what the forest looks like. So the horizontal axis is distance or velocity or frequency. They are all equivalent in cosmology, as you know. And this is the transmission from a background object. So you can see that when transmission is 1, you are seeing full flux from the background object. When transmission is less, you have an absorption line. So what's happening is that in this one-dimensional distribution from a cosmological simulation, the dark matter density is distributed like this. The corresponding gas density is distributed like this. These two are solutions to the perturbation equations that Tirth wrote. Okay, you see they are different. That's the Jeans smoothing term that Tirth explained. Okay, that's the difference between these two. You can see this thing is so sharp in dark matter, it is blunted and smooth here in, this is the pressure term which Tirth was explaining, right? But as soon as you have gas and dark matter, what you can do is combine them with velocities and the void profile for the cross section, Lyman alpha cross section of the hydrogen atom, and you get this. Let's ignore these two middle panels for the moment. There are some technical details that I will need some time to explain. But then this is the Lyman alpha forest. And the beauty is when you do these simulations, there is a precise agreement between this and the data. One of the remarkable triumphs of IgM physics, actually. And this is used to measure the best constraints on dark matter models, etc., using this stuff. I guess I will stop here unless there are any questions.
How much part of the universe is being observed in this for this data?
Lyman alpha forest? Yeah, so Lyman alpha forest has been observed very prolifically from about redshift 2 till redshift 6. And there are efforts underway at below redshift. Below redshift 2, it hits the wavelengths that for which Earth's atmosphere is opaque. So you can't see it from the ground. So you need space-based. Sorry. Oh, IPSCI. So this is done on individual sight lines, and this has been done across the whole sky, but on individual sight lines. The number of sight lines at which this is done is by now hundreds of thousands. At extreme quality, this has been done over. So for example, SDSS and BOSS surveys have measured BAOs using this. Tirth explained the baryonic acoustic oscillations. You can measure that using this. Yeah, so the Lyman alpha forest you have to treat with respect. It's very, very accurately understood. You can't break it. If your Lyman alpha forest model doesn't agree with data, most probably the model is, you have made a mistake somewhere in your calculation. Anything else? Yeah.
The radiative transfer equation you showed before, cosmological radiative transfer.
Yeah.
So in that, is the scattering term included, or
Is what, sorry?
the scattering term on the right-hand side? We have
Yeah.
absorption term and just J nu.
Yeah, so
Scattering term will have an integration over.
so
ray.
most of the absorption here is actually scattering. What is happening is that when we call it one man's absorption is another man's scattering. The photons are not coming along your sight line because they are scattered away in another sight line. Essentially, it's that, and this is being quantified by the kappa. And the kappa, there is a bit of averaging there. So yeah, well caught, because I wrote the equation along the sight line, but there is no averaging in the full calculation. Full calculation, kappa is being computed at that location of the box. And how does kappa connect to the scattering physics that you have in atomic physics and quantum mechanics? Those are very simple equations. The kappa is related to the cross section. Cross section is related to your scattering physics. So the best place I know to look at that quickly is chapter 1.
Hello?
Yeah.
Yeah. So this is just a naive question that I didn't understand.
Yeah.
So for the post-TOR universe, you had mentioned that the universe is in a ionization equilibrium, right?
Yeah.
So the rate of the ionization should match the rate of recombination. And I remember that you had mentioned in passing that there are sources that are still ionizing the IgM continuously to keep this in equilibrium.
Yeah.
But in the start of your talk, you had mentioned that observation doesn't seem to like see any galaxies, especially in the post-TOR universe, that has that potential to ionize.
Yeah.
So how do these two things match?
Yeah, very well noted. Yeah, very good. Yeah, so the biggest chunk of the answer is AGN. So it turns out that there are almost no AGN in the epoch of reionization, which is where there we mostly talk about stars. But at redshift about 2 to 3, the AGN number density is very high. So the universe is full of these supermassive black holes which pump this background. So this background is produced by that. The second thing is, as I was saying, it's not correct to say that no galaxies produce ionizing photons at all. Galaxies are really bad at producing ionizing photons, but some of them do manage, as I was trying to clarify. So that is that contribution. But yeah, well spotted. That's right. So that resolves that inconsistency. So for example, if you look at the Hart-Maddow paper, they will have an integration on the quasar AGN luminosity function. And then they will have an integration on the galaxy luminosity function with an escape fraction. Yeah. Anything else? Otherwise, I think we have clocked 90 minutes. So maybe let us draw this to a close and maybe go for lunch. Okay, thank you.